Yes.
Yes.
Okay. Okay. So let's begin. So in the last lecture, sorry. So in the last lecture, we derived the SUSY algebra. So in the last lecture, what we derived in the end was that Q dagger is equals to H Q and Q dagger is equals to 0. This is the SUSY algebra. I gave this as a homework. I hope you guys checked it. So I want to. We also noticed another thing, uh, that given a bosonic state, let me call it psi boson at energy E, we can find a fermionic state psi f at same energy. How to check that? So I assumed Hamiltonian acting on the psi boson is E times psi boson. So it's a state with energy E. Now if I take another state, take psi fermion to be, should I write a proportionality? Okay. Taking psi fermion as Q times psi boson, then Hamiltonian, because when Q will act on psi boson, it will give me a fermionic state. So this state I am calling as a fermionic state. This is my fermionic state. So now if H act on this Q times psi boson, what will we get? Also, we noticed in the SUSY algebra, we also noticed that H and Q commute. So since H and Q commute, I can rearrange this as Q times H acting on psi boson. And from here, we know H acting on psi boson is E times psi boson. There is a Q. So this I can write it as E times Q of psi boson, which is basically E times psi fermion. So basically psi boson and psi fermion have same energy E. So states with, so here I assume that E is not equal to 0. If E was 0, then this side, the right hand side will be 0. So the states with non-zero energy not equal to 0 are always paired in a supersymmetric system that is for all energies we will have a fermion correspond, we will have bosons and fermion at, we will have boson and fermion so for energy E we will have a boson and a fermion. Now when I said this argument doesn't work for E not equal to 0, let's check it basically. So this argument doesn't work for zero energy state. Why? Let's check. So I'm saying this, let's say that, let's consider psi as a zero energy state. this can be either bosonic or fermionic. You can, for the moment, let me say that it's bosonic, but if it was fermionic, then also the same argument would have worked. So with zero energy state, what I mean that H acting on psi is 0, which implies psi H psi is 0. I have just taken the expectation value, which basically will say psi. Now H I can write as Q dagger plus Q dagger Q, because H was the anti-commutator of Q and Q dagger. Psi is 0. This term I can write it as psi Q. So this term is Q dagger psi mod square plus Q psi mod square. This should be clear, no? Because the first thing is the expectation value of this. If I take the mod square of this will give me Q times a ket. Okay, so since both of these are squares, this means that each term is 0. So Q dagger psi is 0 or Q psi is 0. So if psi was bosonic, then the corresponding fermionic state had to be Q psi. But Q psi is 0. So you don't know whether the fermionic state will be there or not. So what it means that for zero energy states, the corresponding super partner, supersymmetric state or super partner, can be missing. It can be there or it cannot be there. You don't know. So if the psi is a bosonic state, you cannot always apply Q on psi to get a fermionic state. There can be another fermionic state, psi f, that you don't know. But if you start with a bosonic state, you cannot zero energy state. You cannot get a fermionic zero energy state at zero energy by just applying. So what we have concluded for a supersymmetric system, except zero energy states, fermions and bosons are paired. Any question? Okay. Now you know that we have not been able to measure supersymmetry experimentally. So there are two possible things. So supersymmetry is not measured yet, but we know that it solves some of the field theoretical problems. So what people think that there can be two possible reasons, or maybe let's say three reasons. So one of the reasons is it's explicitly broken, so that the world we are living in is not supersymmetric. So what explicitly broken means that SUSY is not preserved by the Lagrangian or the Hamiltonian of the world we live in, of our universe. So this can be one possibility, that SUSY is explicitly broken. Since supersymmetry makes a lot of computations easier and solves a lot of problems, some people, when they work with explicit breaking, they say that it's broken just mildly. It's not fully broken. So what people write is a Lagrangian, which is SUSY, which preserves SUSY, plus a term, let's say, which breaks it, but this term is small. Because then you can use the power of supersymmetry, and also you can solve a lot of issues like hierarchy problem and all. But then there can be another case, which means the SUSY is spontaneously broken. So I don't know if you guys know what it means for a symmetry to be spontaneously broken. Let me just tell you in few words. So what spontaneously broken means, that the Hamiltonian still preserves SUSY. So H and Q still commute. Hamiltonian or the Lagrangian preserves SUSY, but the ground state doesn't. Does not. So if you have a symmetry and the ground state preserves that symmetry, what it means is that when you act the generator, let me say T is the generator of a symmetry. If the generator of the symmetry acts on the ground state, then the ground state it should preserve that symmetry. So this should go to 0. But if the ground state doesn't preserve symmetry, then you say that the symmetry is spontaneously broken. So so from the Hamiltonian, if you take the Hamiltonian or the Lagrangian, you do supersymmetry transformations, it will preserve supersymmetry. But then when you compute the spectrum and then you check for the ground state, if the ground state preserve the supersymmetry or not, then you find that the ground state doesn't preserve supersymmetry. Then we say that the symmetry is spontaneously broken. This happens in our universe. Actually, in standard model, the symmetries of the Lagrangian are spontaneously broken by Higgs mechanism. This is how things get mass. So if you don't know what it means for the symmetry to be spontaneously broken, it's fine. I just wanted to tell that if Hamiltonian preserves SUSY, but the ground state, Q acting on the ground state, is not 0, so it doesn't preserve SUSY, then it is spontaneously broken. So take this as the definition of spontaneously broken symmetry. I think in QFT2 or QFT3 course, you will know the consequences of this thing for standard model. Not about supersymmetries, but other symmetries being spontaneously broken, and it's a very useful concept. So since we expect that in our universe, either SUSY is explicitly broken or spontaneously broken, it's a good question to ask. So it's a good question to ask, if given a system, can we define a quantity which will tell, so given a system meaning given a Hamiltonian, can we define a quantity which will tell whether supersymmetry is spontaneously broken or not? So this is the thing we want to know. So if I have the Hamiltonian, whether it's explicitly broken or not, I can just apply supersymmetry transformation on the Hamiltonian and check whether the commutator is 0 or not. So I can check explicit breaking directly from the Hamiltonian. But in order to know whether it's spontaneously broken or not, one need the full spectrum and all. So the question we want to ask, whether there's some other quantity that is easier to compute, that we can compute, and that quantity can just tell you whether supersymmetry is broken or not. And the answer is yes. And the quantity is called Witten index. Yeah. So okay. So if I want to check whether the ground states preserves SUSY or not, what it means to check. So if Q acting on the ground state is 0, so SUSY is not spontaneously broken. This implies the ground state. This implies that the ground state has 0 energy. That is, Q psi ground state mod square will be 0. If I assume that q psi square is 0, this implies psi ground state q dagger q psi ground state is 0, which will imply that the Hamiltonian acting on psi ground state is 0. So the energy of the ground state is 0. So checking if SUSY is spontaneously broken or not is equivalent to check whether there is a zero energy state in the system or not.
Diksha, just 1 second.
Yes.
Yeah. So this is for the participants. I think like if you have some questions like related to what Diksha is writing, you can raise your hand and ask her also. Okay, because I think that would be useful. Because otherwise, because she definitely cannot keep an eye on the chat box, right? So if something is a generic issue, we can discuss in the chat box. But if something, for example, I think like services questions are very specific to what Diksha is writing. So Sarvesh, you can raise your hand, and then you can Mukta, you keep an eye on who are raising their hands, and then they can ask questions to Diksha.
Okay.
Sarvesh, you can unmute yourself and ask.
Yes.
Yes, the symmetry generator for the supersymmetry. Why does it act on the ground state to give 0? This I do not understand. If it is not broken.
No, so this is the definition of a symmetry being spontaneously broken. So if the symmetry is spontaneously broken, so this we already know that the ground state is, if the ground state has zero energy, it should be annihilated by Q.
Yes.
No?
Yes.
So if a symmetry is spontaneously broken, then by definition you want that the ground state preserves that symmetry. So the ground state, when it acts on your super, if Q acts on your ground state, then it should Q should annihilate the ground state. If that doesn't happen, so in a lot of supersymmetric systems that doesn't happen. If that doesn't happen, it means even though the Hamiltonian was preserving supersymmetry, but the ground state is not, so supersymmetry is spontaneously broken in the system. This is the definition of a symmetry being spontaneously broken, which is different from the system not having that symmetry at all. That is called explicit breaking.
So if the symmetry is not broken, then Q acting on ground state should be 0, na?
Yes.
So what have you written below this Witten index statement?
So the Witten index says, so I am saying that if SUSY is not spontaneously broken, if it's not spontaneously broken, then Q acting on the ground state should be 0.
Yes. Okay. Okay. Yes.
Any other question?
Abhishek has a question. Abhishek, go ahead.
Yeah. Hi, Diksha. So I had a confusion. If the supersymmetry is spontaneously broken, does this still not mean that particle-like excitations which have non-zero energy still have to come in Bose-Fermi pairs with the same mass?
Yeah. So if it's even if the supersymmetry is spontaneously broken, the Bose-Fermi pairs will still be there because your Hamiltonian is still SUSY invariant. So you can always get a Noether charge Q from the Lagrangian because Lagrangian is still invariant. And when you act it on the state, on a bosonic state, you will get a fermionic state.
Does it have to be in the same mass, even if the symmetry is spontaneously broken?
If the symmetry is spontaneous, no, I think they will be of the same mass. No, sorry if I'm saying wrong. One second.
Which is what confuses me because one of the explanations given as to why we don't observe supersymmetry is that it's spontaneously broken. But your argument seems to say that even if it's spontaneously broken, they should still come in with the same mass.
No. So sorry. So if it's spontaneously broken, then you will have the Goldstone boson corresponding to it. No, then then the sorry.
Yeah, I think then it is important, like now, if with respect to which background you are writing down your theory, right? If you are writing, so your I mean vacuum expectation value, whatever it is for your ground state, if your ground state is not invariant, if the symmetry is spontaneously broken, then you have to rewrite your theory with respect to this new ground state, and there you will only have some remaining set of symmetries there. So the part of the symmetry that is broken, with respect to that symmetry, whatever is its consequences are, that will no longer be true for the resultant theory.
Yeah, it's also nice to see it from the example of standard model, no? So initially you didn't have U1 electromagnetism symmetry, but it's when you get when the original symmetries are spontaneously broken to U1 electromagnetism, and those are the charges that you observe in the system, no?
Yes, in other words, I mean, earlier you had more conserved charges, but in the resultant theory you have less number of conserved charges, right?
Yes.
In standard model, I mean, until you broke the symmetry, there were more symmetries in your system, right? SU2 cross U1 is what you have, but after that you see that like it is really broken to just a U1, and then you have less. Only the final remaining U1, the conserved charge corresponding to that, will survive.
And that is the conserved charge that you observe in the experiment.
Yes.
So
yes,
it depends at which scale you are measuring the system, at which energy you are measuring the system. If you are measuring the system, so when a symmetry is spontaneously broken, you get a scale at which the symmetry is broken, and if you observe the system above that energy scale, so at a higher energy than that, then you will see all the symmetries. But if you observe it below that energy scale, then the symmetry has been broken already, and hence you will not observe those charges. So similarly, it will happen for the supersymmetry, that you will get a scale at which SUSY is spontaneously broken. If you measure things above that scale, then you will get the Bose-Fermi pairs and all. You will get all the properties of supersymmetric system. But if you observe the system below that scale, then you will not.
Yes.
Okay. Any other question?
Sorry, I didn't understand the conclusion of the previous question. So, will I have boson-Fermi states of the same mass or not?
It depends at which energy scale you measure the system.
So you're saying that there will be some energy states in I mean, depending on the energy, there will be boson-Fermi states of the same mass, and
no, depending on the energy scale of your measurement. If you are measuring your system at an energy scale where the symmetry is not broken, then of course you should get
is that energy scale the energy scale of the state, or what?
No, it's the energy scale of wherever you are doing your experiments. Right?
I don't understand. What does it mean that what is my energy scale?
See, you have a theory. You are writing down a theory. You are expecting some, I mean, your theory, when you are saying that I am writing down a theory, you are already saying that it comes with a certain energy scale where I am going to measure this, I mean, where I am going to perform my measurements, and my theory is going to give me the expectations correctly to that energy scale. So if you have written down a theory where SUSY is there, I mean where your theory is supersymmetrically invariant and it is not broken, and you are making your measurement to that energy scale wherever you have written your theory, then of course you should get Bose-Fermi scales. But then if you are
of the same mass,
yes, of the same mass, because it has the symmetry, no?
Okay.
But then if the symmetry is broken, right?
But I don't understand what you mean by it has the symmetry. Like I am taking a supersymmetric theory, but the ground state of my theory is breaking that supersymmetry.
So what is spontaneous symmetry breaking? Spontaneous symmetry breaking is your ground state is not invariant under that symmetry.
Yeah,
right?
I understand.
And then what do you do in that scenario? You rewrite your theory around this new ground state.
Yeah, where there is no supersymmetry.
When you do that, then your resultant theory definitely does not have the entire symmetry that you started. Symmetry is broken, right? So suppose your
my question is, suppose in that new theory, my question is, suppose in that new theory I start with a bosonic state and I act on it the Q charge, which is the symmetry of the Lagrangian. What happens then?
Yes. Your Lagrangian has also changed, right? I mean, now you are writing down your theory and around this new ground state. So your entire effective theory has now changed, right? Now, and your effective theory does not have the full symmetry of the parent theory.
I understand it might not be a symmetry operator. I'm just asking what happens when I act Q on that state.
So Arindam,
Yeah.
So Arindam, that's since this it's general, this discussion is general. So take any symmetry which is spontaneously broken.
Yes.
Then that means that if the symmetry acts on the vacuum, it gives a different state, which is also a vacuum, right?
Right.
Which means that if you take an excited state around the first vacuum and act with the symmetry generator, you get a state around the different vacuum, an excited state. You do not get a state around the same vacuum.
Right.
So that means if you look at the state around the one particular vacuum, you will not see the degeneracy.
That's true.
So you will get another state.
No. So but in the case of, I mean, what happens is that in that case, I understand that these two states do come with same mass, no? I mean, the energy of these two states are also same. Isn't that this?
They are same, but they are not visible by the perturbative expansion around the same vacuum, because that's a state around the new vacuum. I mean, the whole thing, the states come in multiplets around the vacuum, depends whether the vacuum has the symmetry or not. If the vacuum doesn't have a symmetry, then the state around that vacuum will not come in multiplets. So all the things then doesn't hold. So to summarize, in that case, you will not have Bose-Fermi pair if you look at just the perturbative spectrum around that particular vacuum.
Right. Okay. Yeah. That was my question. I guess.
Can we say that if a symmetry is getting broken, it does not matter if the symmetry was ordinary or a supersymmetry? It's the same thing.
The spontaneous broken story that Diksha said, that discussion is true for any bosonic or fermionic, doesn't matter. It's the same story actually.
Yeah. But there is a difference between explicit breaking and spontaneous breaking. The difference comes because for a spontaneously broken symmetry, it is possible to at some high energy scale, it is possible to regain the symmetries back of the system, and you can see that the original Lagrangian obeyed that symmetry. But for explicit breaking, the original Lagrangian itself did not obey that symmetry. So,
sorry, I have last question regarding this. So
yeah.
when, for instance, I take an excited state around a chosen vacuum, which breaks the symmetry spontaneously, and then I act Q on it, I understand that it will go to some excited state of some other vacuum. But can I expand that state in terms of the excited states of this old vacuum that I had?
Not perturbatively.
Oh, okay. Okay.
It will be some tunneling effect times this thing, and tunneling is non-perturbative.
Right. Okay, I understand. Thanks.
Okay. Any other questions? Okay. Let me go ahead. So checking if supersymmetry is spontaneously broken or not is equivalent to checking whether there is a zero energy state in the system or not. This is what we concluded, no? So now we want to define a quantity which can tell whether there will be a zero energy state in the system or not. Why I need to define a quantity? Because given a Hamiltonian, it's very difficult to compute the whole spectrum. But if I can define a quantity which might be easier to compute, I'm not still telling whether it will be easier to compute or not. But if I define a quantity which might be easier to compute than solving the full Hamiltonian, then it's nice to have a quantity whose value will tell you whether there will be a zero energy state or not. In other words, whether supersymmetry will be spontaneously broken or not. And this quantity is called Witten index. So let me just define the Witten index. So Witten index is defined as trace over the Hilbert space of the system minus 1 power f exponential minus beta times Hamiltonian h. Here beta is the inverse temperature. Okay, the temperature at which you are doing the experiment, and f is Fermion number. So exponential minus beta h. This is just trace over exponential minus beta h. This thing is just a partition function. No? If you guys know what's a partition, this is the definition of a partition function. Now I have added, but instead of computing trace over Hilbert space exponential minus beta h, I have added a operator minus 1 power f in front. And what does this operator do? This makes the partition function. This you call it a supersymmetric partition function also. Supersymmetric partition function. So what this operator does in a path integral, if I have time in the last lecture, I will tell, I'll explain, I'll elaborate on it more. This basically, this thing provides same boundary conditions for fermions and bosons, hence it's called supersymmetric. But anyway, so this is just a modified partition function. Let me call it that. So Witten index is basically trace over Hilbert space minus 1 power f exponential minus beta h, where f is fermion number. So how f acts? So if minus 1 power f acts on a bosonic state psi b, then you will just get psi b, because f will be 0, and so you won't get any sign change. But if minus 1 power f acts on psi fermion, then it will be minus psi fermion, because f will be 1 in this case. So for the bosonic state, you get the same sign. It doesn't change sign, the minus 1 power f operator. The fermionic state, it changes sign for minus 1 power f operator. So basically what you are doing in this trace, so the Witten index, let me call it W of beta. So W of beta, which is trace over the Hilbert space of the system, minus 1 power f exponential minus beta h. This you can write as number of bosons of energy E exponential minus beta of energy E minus, sorry, let me write one more step. This trace you can write it as sum over I, sum over the states I, psi I minus 1 power f exponential minus beta h psi I. This is the definition of the trace, where you sum over the whole spectrum of the Hamiltonian. Now, if the ith state, if a state is a bosonic state, so that is NB. So if you have n number of bosonic state at energy E, you will get NB of E at energy E exponential minus beta E. But for the fermionic state, you will get a minus sign. So minus NF at energy E exponential minus beta E, and then you sum over all energies.
Diksha, Arpita has a question. Arpita, can you ask?
Yeah.
Yeah, that H was like Q dagger Q plus Q dagger, na?
Yes.
But here you just took it as Q dagger Q. So
Where?
just last
No,
one, I just missed it. So about that reason I'm asking.
No, it's equivalent in the sense that if this term is 0, then because both these states are the same states, then also this term is 0, no? Psi ground state, Q dagger and psi ground state. So this term is also 0. So if this term is 0, then this term is also 0. So the sum is also 0. So I just skipped the step. This you can write as half of the Hamiltonian.
Okay. Yeah.
Okay. So here, so you sum. So I hope this step is clear. This step, what it basically says, that for if psi was a bosonic state, then you will get with a positive sign, because minus 1 power f will give you a plus sign, exponential minus beta of energy E. If the n bosonic state at that energy, you will get the number of bosons at that energy times this. For the fermion, similarly for the fermionic state, you will get NF, which is the number of fermionic states at that energy, exponential minus beta E. Now we also know what I have told. So if this is energy, so for any non-zero energy, if I have a boson, let me say this is a boson, I can apply the operator Q to get a fermion at that energy. So if I had two bosons at some energy, I can apply Q to one and then Q to another to get the fermions at that energy. So for E not equal to 0, bosons and fermions are paired. and paired. This means that for all non-zero energies, since bosons will come with a positive sign and fermions come with a negative sign, both of these things will cancel from the trace. So bosons come with positive sign and fermions with negative sign. So since bosons come with positive sign and fermions come with negative sign, both for non-zero energies, bosons and fermions will cancel from Witten. Bosons and fermions will cancel from the trace. So the Witten index now will just be number of bosons at energy 0. Now they will be exponential minus beta. If E I put as 0, this term is 1. No? So I'm removing this. Minus number of fermions at energy 0. Is this clear? Okay. So the Witten index is number of bosons at 0 energy minus number of fermions at 0 energy. Now if Witten index is not equal to 0.
Sorry, I have a trivial question. Can I just ask?
Yes, yes.
So at any energy level, shouldn't the number of fermions be at max 1?
No. So in the example I was telling yesterday, I just considered a very simple system where there was only one quantum number distinguishing two states. But if let's say you have a hydrogen atom, there you have 4 quantum numbers, but energy is determined only by one quantum number. So you can have multiple fermions which have different quantum numbers. So they obey Pauli exclusion principle, but still they have same energy.
But the system, for instance, you are considering here, it doesn't have any other distinct quantum numbers, right?
So yesterday I was talking about a one particular system, but all the things I'm telling today is valid for any supersymmetric system. So now I am not assuming that there is only one quantum number. So all the things I have told today till now today are valid for any supersymmetric.
Sorry. So yeah, but I understand that. But even with all the quantum numbers, what I'm trying to ask is probably that the number of bosons that are allowed to be in one particular energy state is always greater than the number of fermions allowed to be in a particular energy state, right? I mean, why is the number same? This is something that I'm not guessing. I understand.
Because of supersymmetry. Because if you have a boson at a particular energy, then you can always get a fermion at that energy. Now, if you had, let's say there was only one quantum number n, distinguishing fermions and bosons, then if you have a boson, one boson, that's a psi boson, then you will have one fermion. But now you are saying that you cannot have multiple fermions at the same energy level. So you will not have multiple bosons at that energy level. This is the power of supersymmetry. So your system is built in that way. You will only have one boson there in that case.
Yeah. So what you're saying probably is that if I, for instance, try to find the occupancy distribution of bosons as well in these supersymmetric systems, I'll get a statistics I'll get something like a Fermi-Dirac statistics even for them.
Okay. This I don't want. Okay, let me think for a moment.
Because if so, then I do not know why would I call them bosons. No?
No, the statistics doesn't change.
And if the statistics doesn't change, then the occupancy number cannot be the same for bosons and fermions because the statistics is clearly different.
I am not understanding. Sorry, Arindam, can you come again, please?
Yeah, my question is that suppose I take a supersymmetric system.
Yes.
And I just want to calculate the occupancy number of bosons for every energy state.
Yes.
Right? I can calculate that separately.
Yes.
I can calculate the same for fermions.
Yes.
What will I see? What will be the statistics of these two? Will they be same?
Both Einstein and Fermi-Dirac, yes.
There'll be Bose-Einstein and Fermi-Dirac for different ones, right?
Yes.
But they are not same.
No, but what Diksha is computing is not exponential minus beta h, but minus 1 to the power x exponential minus beta h. It's a twisted partition function.
No. That I understand. She is considering both bosons and fermions. I'm saying that I can calculate just the occupancy number of bosons and just the occupancy number of fermions, right?
Okay.
For a particular energy state. Those are not same.
For a
So what does it
particular
mean?
wait, for a particular energy, they are same.
They are same.
Yes.
No, Bose-Einstein statistics and Fermi-Dirac statistics doesn't give the same result.
That is a sum over all the energies, right? All the states.
Sorry, no. There is a in the previous lecture also she talked about the occupancy number at a particular energy state, you know.
Yeah. It's not, there is no sum. There is the expectation
there is no
value of
sum.
all
Yeah.
particles at an time. No, but that is the probability distribution. That's the part that's confusing.
But even the probability distribution should come same. If I'm saying that for the number of bosons and the number of fermions in a particular energy state is same, then the probability distribution should also be the same. I mean, it should give the same result.
I think the answer can be that what we are defining here as bosonic and fermionic states are not bosonic and fermionic particles. Like for example, in the last lecture, she had said that a state with an even number of fermions is also a bosonic state.
Then I do not understand what we mean by bosonic and fermionic states.
Arindam?
Yeah.
Hello. I have a comment. Like for in many particle system in condensed matter also, you can have n number of fermions, n number of bosons, and the bosons follow this bosonic statistics, and fermions follow this fermionic statistics. What Diksha is trying to say, I think, the type of fermions and the type of bosons, they must be same, or they must be different at different energy scales. That is, is it true, Diksha?
I didn't understand the type of fermion. What does it mean?
Yeah, N, B, and N, F. These are type of fermions at certain energy scale. Like for example, for a photon, you can have one super partner at, and for some boson, some fermion, you have some the super partner, bosonic super partner, but the number of those partner can vary at different energy scales, right? It is not total number of fermions or total number of bosons and some particular energy scale.
No. If you have one supercharge, then you will have one fermion corresponding to one boson.
So
the number will be same. So the number, the difference in number comes when you increase supersymmetry and all. So if you have only one supercharge, so the part is confusing is sorry, what?
NB is occupancy number or type of bosons or type of fermions, and NB and NF.
NB is the number of fermions at that energy level.
Okay. Then regarding this fermion statistics and Fermi-Dirac statistics and bosonic statistics, it should not be problem. Like you can have some n number of fermions or n number of bosons or some pair of these things, and you can have statistics corresponding to them. Like it always happens in many particle systems in condensed matter.
Okay. No, but
Right.
I have a comment to make regarding Arindam's question.
Yes, go on.
Yeah, I mean, what Arindam asked, Arindam, I don't see why, when you talk about Bose-Dirac or fermion statistics,
yeah,
it's just you are given an energy level, you are trying to figure out NF and NB. When you are talking about supersymmetry, there is a ground state with actions of operators on it. The NF that you get is not produced by action of, like, none of these fermions are coming from some vacuum or anything. You are given some spectra, you are just trying to distribute some particles in boxes, basically. Right?
That is true. But what they are saying here is that the number of bosons I can distribute in each box is the same as the number of fermions I can distribute in that box, no?
No, this is type of fermions and type of bosons. It's not occupancy, I guess.
Sorry, I think.
Right, Diksha? Or wrong?
Yeah, sorry, I think I.
Degrees of freedom should be same.
Yeah, it's degree of freedom. So it's basically saying that if you have a system, if you have 4 fermions, and then if you have a system, you know there are 4 fermions, 4 bosons, and there's 1 boson at this energy, 2 bosons at this another energy. Now you have then you will say that there is 1 fermion at the ground state and the 2 fermions. So here you have already fixed the number of particles.
But so for instance, I start with a bosonic system, and I say that there is one excited state which has no degeneracy. Okay, so I have this complete set of commuting observables, which is saying that there is only one state there at that energy level. Yeah. So at that energy level, suppose I have 2 bosons, right? So the if I act the supersymmetry generator on it, now that energy level should have 2 fermions.
Yes.
Which shouldn't be the case, because given there is no degeneracy, that energy level should not have.
No. But you can have 2 types of fermions, but they will occupy different state. But bosons can occupy same state.
But then you won't be able to even put 2 bosons in that energy in that box.
So, you're saying I won't be able to put 2 bosons in that box?
Or in the.
Mm-hmm.
Yeah, I mean, if you take an ensemble of bosons and fermions,
right?
Okay, you can have different configurations in the system,
right?
At finite temperature,
right?
And you will have this NB and NF, the occupation numbers. For that, the number of particles, bosons in different energy levels, number of fermions in different energy levels.
Right.
Now, if you consider a configuration which is supersymmetric, which has the supersymmetry,
right?
For that particular configuration, I think NB should be equals to NF for all E.
Yeah, but then that means that they'll either deviate from the Bose-Einstein statistics or Fermi-Dirac statistics, or both.
Sorry, say again.
I mean, in order for NB to be equal to NF at all energy levels, they will either differ from the Bose-Einstein or the Fermi-Dirac, or both.
Why are you telling that?
Because Bose-Einstein and Fermi-Dirac doesn't allow NB to be equal to NF. If I assume that NB follows the Bose-Einstein statistics, NF follows the Fermi-Dirac statistics, then NB cannot be equal to NF.
NF is between 0 and 1, right?
Yes.
And what about NB? Is greater than 1.
It can be greater than 1.
No, it can be greater than 1, but it can also be
less than 1. That is true, but if you follow Bose-Einstein statistics, given the degeneracy and the energy of the system and the temperature, it's fixed, right? And it can be greater than 1.
No, it can be not. I'm asking, it can be greater than 1, but can it be less than 1?
Can it be? You mean 0? Yeah, it can also be 0 or 1.
So I think, sorry. I think the confusion.
No, I think first of all, you have to consider the average, right? Average can be fraction.
So if you just look at all the fermionic states in what Diksha in this definition, and you go from one to another by action of a bosonic operator. So here fermionic means it's just a fermionic grading. It's not really fermions and bosons in the way we think about in the Fermi-Dirac statistics. Right?
Then what's the definition of fermion? Sorry, I didn't understand.
I mean, here the definition of fermion, you define an operator -1 to the power f. And if it gives you 1, you call it boson. If it gives you -1, it's a fermion.
Yeah,
So
but there is some reason that I'm calling that
fermion.
No?
It is basically composite. It consists of one fermion and multiple bosons, right?
Yeah, that's okay.
Yeah, so the sum over states is actually a sum over bosonic states, because fermion number is kept at 1 only.
Oh, okay. I understand what you're saying. So you're saying that by just applying Q, what I'm doing is that I'm taking a bunch of bosons and putting one fermion in between.
One fermion. Yeah, I am
Yeah,
never
yeah.
changing the fermionic
Yeah.
thing. So that's
Yeah,
why
yeah,
it's
yeah,
basically
right,
both
right,
of them
right.
are Bose-Einstein statistics.
That's true. That's true. Yeah, yeah, I understand. Yeah.
Sorry, what is the thing? Sorry, say again or no?
So what I said is basically this. So I had NB and NF could only be 0 or 1. So if with a Q, I went from NB this state to a state which was NB and NF1. So and
Yeah.
I call this as a fermionic state. But NB can be any number.
Yeah, this is
So
fine.
Yeah. So it does follow Bose-Einstein statistics, and then you just add one more particle with it for the fermionic
one
state. One fermion with it. Yeah. Yeah, yeah. That clarifies it.
very
Thanks.
good question. Thank you. I didn't think about it.
Yeah. Yeah. It's,
Very
thank
good
you.
question.
So your last state satisfies this formula statistics. Sorry, I mean I didn't understand what is the statistic satisfied by.
No, so this state has only number of bosons, and the bosons in this state will anyway satisfy Bose-Einstein statistics. There is one fermion, which
Right.
the fermion satisfying the Fermi-Dirac statistics. So
Yeah.
here, this part is still satisfying the Bose-Einstein statistics, and there is no fermion, so there is nothing satisfying Bose-Einstein.
Diksha, the
Yes.
collective.
Yes, I cannot.
I'm asking that this RHS collectively it is following Fermi statistics or not? Like this NF is following the Fermi statistics, but whole
Collectively, it behaves like a fermion because if you have let's say wave functions, no, if you have two
right,
bosons,
then
one
it's
fermion.
okay.
And then if you interchange them, you will get a negative sign, no?
Right, right.
You will psi one psi fermion.
Mhm.
Sorry.
So same
You
thing
won't
happens in atomic physics also. Like some atom is behaving like a fermion if it has one like unpaired electron or something.
Yes.
Okay.
Diksha, then what do you mean by NB equal to NF?
No, so this is at a particular energy. So the state I am writing has energy square root of NB.
Yes,
Yesterday
yes.
we
Even I'm also talking about a particular energy. Yeah, the particular energy, then what do you mean by NB equal to NF?
So if there is only one quantum number, okay. So
Yes,
if
that's energy.
so this NB and the NB I have written here is different. Sorry, I'm using the same notation. So I am calling. Uh, let me call something. B is boson and F is fermion, and here F is 0. So here this is B, comma F is equals to 1. This is Q. So the number of such states, I'm calling as NB, and the number of such states, the total state, I'm calling as NF.
Excellent. Okay, go ahead.
You know? Yeah, sorry, I was
Yes.
using the same everywhere.
So their numbers are really set. So NB is really equal to NF.
Yes,
I
the
mean,
number.
whatever is the NB that you wrote is really equal to NF.
Yes.
Yeah, go ahead.
And this is true for any B.
This is true for any energy. Yeah. I mean, other than equal to.
Any B. Yeah, any energy.
Yes. Okay.
Diksha, can you remind me in the context of the supersymmetric harmonic oscillator what you were discussing yesterday? Why
Yes.
NB and or whatever B and F equals to 0 state and B and F equals to 1 state have same energy?
Okay. This thing is here. So, I applied Q, you get this, and then if you, sorry, maybe I gave it as a homework. I don't know if I did the same
Hamiltonian
thing.
commutes with Q.
Yeah, Hamiltonian
No, sorry.
commutes with. Yeah.
Sorry,
So,
just go up. So Q acting on that. So okay, Okay, your bosonic, okay, number of bosons is reduced by 1. Okay, fine, go ahead. Okay, fine.
Yeah.
Yeah, okay. So, yeah, so, okay, fine, yeah.
Okay.
Number of boson is reduced by 1.
Yeah, because Q has A, the annihilation operator of boson, and the creation operator of fermion, AB dagger, and Q dagger is the opposite. It will be A dagger. Okay. Okay, so if the Witten index is non-zero, then this implies that there is at least one zero energy state. There can be more, but at least one zero energy state. So if there is at least one zero energy state, that will be the ground state. Hence the ground state will have zero energy. Since the ground state will have zero energy, then supersymmetry is not spontaneously broken. This is what we concluded, no? But if the Witten index is zero, it can occur from two different cases. One is that number of bosons at zero energy is equals to number of fermions at zero energy, or there is no zero energy state. Only in this case we know that the supersymmetry will be spontaneously broken. But here, in the case above, you still have zero energy state. So supersymmetry is not broken. So if the Witten index is zero, you cannot conclude anything. So you cannot tell. So you cannot tell whether supersymmetry will be broken or not. So what I concluded is that if Witten index is not equal to zero, this definitely implies that supersymmetry is not spontaneously broken. But if it is equal to zero, then you don't know. So this is a quantity that you can compute. Now, if you want your theory to break supersymmetry spontaneously, then you demand that the Witten index should be zero. So if the Witten index is not equal to zero, so if you are given a theory and somebody asks you whether it breaks supersymmetry spontaneously or not, whether it breaks supersymmetry or not, there are two things you have to check. One, given the Hamiltonian, you check whether Q commutes with the Hamiltonian. So whether SUSY is preserved by the Hamiltonian. If that happens, then you check for spontaneously breaking. If you want to check for spontaneously breaking, you compute the Witten index. And if its value is non-zero, then you know it's not broken, spontaneously broken. If it is zero, then you cannot conclude anything. So Witten index is a quantity that tells you about SUSY.
Diksha, there is a question.
Yeah.
Sorry, isn't it the opposite? If Witten index is not zero, supersymmetry is spontaneously broken.
No, it's usually it confused me for a long time. Sorry, so let me go again. So Witten index, what we concluded was the difference between bosons and number of bosons and fermions at zero energy. And we already noticed that the zero energy states need not be paired, because when you apply Q operator on a zero energy state, you get zero. So you do not get the corresponding fermionic or the corresponding bosonic state. So it might be paired or it might not be paired. You do not know. So if the Witten index is non-zero, this will say that there is at least one zero energy state. Even if they are not paired, but there is some zero energy state. So if there is a zero energy state, that will tell you, as we already discussed, a zero energy state will say that Q acting on that state will be zero.
Yeah, okay. Sorry. You're right. Yeah.
So then the supersymmetry is not spontaneously broken. But if Witten index is zero, in that case, you cannot conclude whether there is no zero energy state or whether there are zero energy state, but the bosons and fermions are paired. You cannot say. There can be two cases. So you not get information.
Thank you.
Any other question?
Deepajyoti has a question.
In the example that we considered last class, In that case, B is equal to 0 and F is equal to 0 state has 0 energy. And
Yes.
according to our conclusion of whether a state will be bosonic or fermionic, whether the state is bosonic or it is fermionic, because it is not fermionic because the fermionic number is 0. But is it
But it doesn't have
bosonic?
any at all. We
Yes, it
cannot.
does not have any.
Yeah. So if the particle number is 0, you can. If there's, it's like a vacuum. No, what will you call a vacuum? A bosonic or a fermionic state? It doesn't have any.
All right, because if you define the index operator like you defined here the NB will be 0, right?
No, no.
When operating
So
on
again,
this state.
no. Again, sorry. I used the same.
1 minute. So typically the assumption is that vacuum is bosonic because a fermionic state means that it transforms under some representation of the Lorentz group. So the moment you assume that vacuum is fermionic, it means that the Lorentz symmetry is spontaneously broken. Experimentally, that is not true. So typically, vacuums are always assigned with bosonic statistics, especially if they're unique. Okay?
Right.
Do you agree, Diksha?
Yeah. No,
Then in this case, not the NB is 1.
I thought the confusion was this. So this NB is the number of bosons, not the. Yeah.
But is not that NB comes from -1 to the power f, and if the vacuum is bosonic, then -1 to the power f should be 1.
No. It's saying the number of particles of 0 energy state. So the vacuum.
Right, it eventually comes from that, na?
No. So
It
in that.
eventually comes from -1 to the power f.
No. In that case, my supersymmetry was not broken. So there, the vacuum was a 0 energy state. But here, it can be a 0 energy state or not a 0 energy state, because for the supersymmetric system, the energy should be greater than equal to 0. So your vacuum could have been a state. So your ground state. I'm not calling it vacuum because vacuum means it's no energy. So your ground state could have been a state which has energy greater than 0. So it could have had particles.
Right. So, but in our previous example, the vacuum state has 0 energy.
Yes, it has 0 energy. The vacuum in the previous example, the vacuum had 0 energy, and if you compute the Witten index for that example, you will find the Witten index is, I think, 1.
So if Witten index is 1,
is plus 1. If you compute the Witten index for that example.
Right. It's not right.
So okay. As an exercise, I think that's a good thing to do. Compute. Because harmonic oscillator, you know the spectrum, no? So you know the spectrum, so you can compute this trace. So compute Witten index for supersymmetric harmonic oscillator. And also compute Witten index for the fermionic harmonic oscillator. No, that's not a good. Okay, try to do this. You will find that the Witten index should be, I think, 1, if I'm not wrong, or there's a normalization thing. Okay. Any other question? Okay, so we have run out of time. I will discuss the next thing maybe tomorrow. Okay, I'm stopping the screen share and then we can discuss if we have questions. Okay. Any questions?
Diksha. Hello. Is this some idea about some experimental value for this supersymmetric scale, energy scale? I guess. I mean, like for experiments. Like LHC and China is also building 100 TeV collider. So
the expectation, so whenever we don't observe something, we say that the SUSY is broken at a higher scale. So we just push the scale.
that is happening. That is also, you know, that is happening from 2011.
Yeah, so the point is, if it's spontaneously broken, we should be able to measure the Goldstone boson corresponding to it. For example, in standard model, we are able to measure Higgs boson, which is the Goldstone boson corresponding to the symmetry weighting. So since we have not been able to measure the Goldstone, I should not call it Goldstone boson, it's Goldstone. It's a fermionic particle. So
Mm.
you're not able to measure that. Symmetry has to be broken at a much higher energy as compared to the galaxy and all.
And my second question is about condensed matter. Is there any kind of observed phenomena which is giving some signature about this kind of supersymmetry, like some analogical system, like that in BEC there is the mathematics is kind of similar to the black hole, which is called sound hole, like some kind of this kind of some signature.
I don't know. Maybe Abhishek would know. I don't know. I don't.
Okay, fine.
So actually there is a recent paper in the quantum Hall systems where people tried to actually derive the Laughlin wave function using supersymmetry. So
Okay,
that's one place I know where supersymmetry is used to compute something which is closer to experimental observation.
So please share that thing that it might be useful to learn some.
Okay.
Okay, fine. Thank you.
Okay. Any other question? I know today's lecture was a bit. There were a lot of not enough mathematics, but there were a lot of concepts, so it might be.
And the discussion it was really good.
That was a good question. I didn't think about it. Okay. Anyway, for tomorrow's lecture, at what time should we do another?
You can ask your question. There is another question, Diksha.
Yes.
Anirban, if you are still here, you can ask your question.
Anirban Majumdar. Anirban, ask your question.
Okay, then I will ask his question. He is asking that can we say if Witten index is greater than equal to 0, is true always at e equal to 0?
No. So sorry. If Witten index is greater than equal to 0, then?
No. His question is at energy equal to 0, is Witten index is always greater than equal to 0?
No. If for Witten index, you need to sum over all energies. So you cannot say that Witten index is defined at energy is equals to 0. You compute the whole trace, no? So you compute the whole partition. You sum over all the states. So it's not defined at a particular energy. So that maybe I didn't understand the question properly.
Can you just look at the chat box? I think you have answered, but just look at the chat box. His mic is not working.
Because fermion has mass, it can't stay at 0 energy. No. So sorry, that was the question. What Navmita said. The question was that can Witten index be, we can say that Witten index is greater than is always greater than equal to 0 is true at energy E is equals to 0. But Witten index you sum over all energies. So you do not say that Witten index is greater than equal to you do not say about value of Witten index at a particular energy. Another question that can be that somebody can ask whether Witten index is always greater than equal to 0 or it can take negative value also. So if the 0 energy state is a fermionic state, your system might be unstable system. But if that is the case, then you can also have a Witten index which is negative. So I can give you, maybe in the next lecture, I can write some Hamiltonians whose Witten index you can compute. And one of, for example, if you compute Witten index for the fermionic harmonic oscillator, even though it's not a supersymmetric system, but you can still define this quantity and compute. And since that system only has fermions, that the Witten index will be negative because fermions will come with a negative sign. So it can have negative value. Okay. Yeah, high energy contribution to the Witten index cancel. Yes, that's correct. Devajyoti. So the Witten index gets contribution only from 0 energy states, but the 0
then
energy
we have to only look at the 0 energy state, right? To find the Witten index.
Yes. No, if you already know that if you already know there is a 0 energy state, then you do not need to compute Witten index to know whether there is supersymmetry is broken or not. So usually it is done when you don't know the whole spectrum, but it's easier to compute the partition function. But if the system is not, let's say if the supersymmetry is broken, it's not supersymmetric. For example, a fermionic harmonic oscillator. No, if you put the Witten index for that, you will get a negative Witten index.
Right. Right. Because that means it has no zero energy, right? Because it has only minus half, or then the other energy it can have is plus.
Energy state, but it has a fermionic zero energy state. That is what it says. If the Witten index is negative, so Witten index is positive. So Witten index tells you, Witten index tells you the number of bosonic zero energy states minus number of fermionic zero energy states. If it's positive, it tells you you have more bosonic zero energy states than fermionic one. If it's negative, it tells you have more fermionic zero energy states.
Right.
Okay. Can Witten index be computed from experiment? It's partition function, no? A partition function you can, I don't know if you can compute it from experiment. No, I don't know. That's the question. Can Witten index?
I think you have to measure the energy to count the number of fermions. Then you can, then this can be done. Maybe I'm not sure.
Yeah, but in an experiment, an absolute energy is never measured. It's always a change in the energy that we can measure as an observer.
Technically, okay. Then.
Is it not related to entropy?
Witten index is related to degeneracy, no?
Yeah, exactly. Degeneracy and hence entropy. Yeah.
There must be some signature. Okay.
It's related to the degeneracy at zero energy, but I don't know how you can measure that using experiment, in the sense that if how you can, like, okay, maybe I don't, if you can measure number of zero energy states, I don't know how.
Entropy?
Entropy? How can you measure entropy experimentally?
Well,
Navamita, even if you can do that, you have to measure whether what is the quantum number by minus 1 power f, right?
Yeah, because look, Hamiltonian H is a Hermitian operator. Hermitian operators are physical observable, so you can measure energy. But
Diksha, in one event you cannot measure, you cannot guess anything. I think you have to do this so many times. Then you will find some statistical signature also, which you can rule out other things. Like already people are doing in LHC and all those things in experiments like this. Like they have some sigma bar that this particle correspond to that thing or whatever. That kind of measurement should be there. Like you cannot be sure in one event. Event, I mean, after colliding, you are measuring different particles, some signature, some experimental signature. Then you have to do it for quite a long time, and you have to you will have some experimental data from that. These are technical details, but leave it. I also forgot all these things now.
No, but another question that one can ask is whether the fermion number operator minus 1 power f, so whether this operator is a Hermitian operator, whether you can measure it or not.
Yes, you can. Yes.
You can measure it experimentally?
Well, minus 1 power f in higher dimension is just simply 2 pi rotation. So you can.
Yeah. Okay, then I think you should be able to measure the whole Witten index, no? Because it's consistent.
But what you are saying is basically measuring the number of ground states and then measuring the statistics and then computing Witten index. So if you mean by that, then yes. But I think Yash was, if Yash is saying asking that, then yes. But there is no other way. I think you can compute it experimentally.
Yes.
Okay. So I can't see any other question. Okay. Okay. Thank you. Yes. Yeah. Any other question? If not, yes. So Diksha, will it be problem for you tomorrow this time?
If it's possible to do it earlier, that will be better. But okay, if the earlier slots are fixed, then it's fine.